try to what is called yeah, they are also trying to insert or give us some new features in Google Meet. So
Yeah.
we are also what is called trying to understand or trying to use the new
Yeah.
features in these apps.
Oh, I
Okay.
am somehow I'm okay. So let me just try to share my window. Let me try entire screen as you said. So let me see how it goes. Can you? Okay. So let me see what is coming out. Can you see the screen? No,
Just coming up,
No,
sir.
no, not. Yeah, yeah.
It's just
coming up.
yet not, sir.
Ah,
Yes, yes. It
can
is
you see now?
coming. Yes.
Yes, yes.
Okay, okay. So let me start then. Let me first recapitulate what we had tried to discuss yesterday. Is that as I said, all of us has done this, you know, quantum mechanics for the particles. So what we did there is that uh, uh, we had situations like photoelectric effect, Compton effect, where we have seen that our ordinary classical mechanics fails, right? Then what we did actually, as I mentioned yesterday, that classical mechanics fails to describe the microscopic world. Like the most famous example is the motion of electrons in the hydrogen atoms or any other atoms. Now, then what we did, we promoted the classical dynamical variables to operators and used these commutation relations and made a transition from classical mechanics to the quantum mechanics. Now, if I take the continuum limit of the classical mechanics, then what we get is the classical field theory. And I gave you an example that if you take a system of particles joined by spring of length A, right? If you want to describe the motion of such a system, you get for n particles, you get n number of equations which describes the motion of these particles. But if I take the continuum limit, that means the length of the spring tends to 0, then what happens? I get a wave equation which describe the classical field theory. Now, what the philosophy here is to identify some dynamical variables what describes this classical field theory, right? And then those dynamical variables will promote them to operators like we did in classical mechanics, and then we'll use certain quantization conditions to make a transition from classical field theory to quantum field theory. That is our philosophy. So what we learned so far is the quantization of particles. In this course, we will discuss quantization of the fields, which will give us the quantum field theory. And this is the system which I have described in detail yesterday, right? And then what we got this wave equation, right? And so that is the philosophy I will follow. But today,
Hello.
sorry.
তাই না?
So this is the wave equation which we got in the continuum limit. Now, what I have to do to fix the notation and nomenclatures, I'll just very quickly go through this special theory of relativity just to fix the notation. I'll not discuss the special theory of relativity as such, but this part is required because, as I said, that the quantum field theory is nothing but it's quantum mechanics plus causality. And causality enters the theory through the special theory of relativity. So special theory of relativity and the quantum mechanics, these two innovations we need to combine in a consistent way, and that's what is quantum field theory. So just to fix the notation, I will discuss a few variables for the special theory of relativity. This is mostly all of these known to you, but just my notations could be different, so I am discussing it. So this space-time coordinate, 4 coordinates, the variable x mu that we write as time component denoted by x0 and x vector, which has a 3 component x, y, z, right? And this x0 we can take as time. Normally it is taken as ct, but c is 1, so then x0 will be just equal to t. And here you have a frame s and another frame s prime, and s prime is moving with respect to a velocity v along x direction with respect to s. Now then we know that from the Lorentz transformation, what should be the transformation law between this frame s and s prime. This x0, as I said, is t, x0 prime is t prime, and x mu vector, this is called contravariant vector, x0x. This, please note that here is a plus sign, plus x, and the covariant vector is x mu. The index mu is a subscript, and it is t minus x. So an x prime mu will be then t prime minus x prime. And we know that the transformation of the x coordinate, because the motion is along the x direction, it is gamma, is famous Lorentz gamma, x minus vt, where v is the relative velocity between the two frames, right? And y prime is equal to y, z prime is equal to z, because the motion is along x direction. Now this transformation, along for the time, that is quite surprising, and but that comes from the condition that velocity of light in vacuum for every frame is a constant. So if you think in this way, that suppose I have a coordinate x, right, certain x in one frame and x prime in the other frame, then if the velocity of light, the signal is traveling with the velocity c, then I can write c as x by t. Now in the new frame, my coordinate is x prime, and if c I have to keep constant, then c is x by t. Now in the new frame, it is x prime. If I keep the same t, then constancy of the velocity will be violated. So if c is equal to x by t in one frame, and if c has to be same in the prime frame, then it has to be x prime by t prime. It's not x prime by t. So the constancy of velocity actually forces that the time should also change in this particular fashion. I'm not going into that detail, but this is the philosophy that the velocity of light, since it is constant in all the frame, so the time should also transform from one frame to the another frame. And these notations I will use, that sometime I will use x as x1, x2 is not x square is y, x3 is z, etc. Now this transformation, this transformation t prime to t and x prime to x and t, I can write in terms of a matrix where x prime mu, where this x prime mu is a 4 vector, its temporal component is time, and the spatial component is a 3x vector, and this x prime is related to another contravariant vector x nu through this lambda mu nu, where this lambda mu nu is just a matrix, and if you put this x prime lambda mu nu here, then basically what we have written, this equation we have written in the matrix form. Okay, so this lambda mu nu is the transformation matrix. This Lorentz transformation, it's like a boost, right? But this can also be, it can also be shown, it is like a rotation in a two-dimensional plane. So if you rotate a coordinate in two-dimensional plane, then you know how x prime and y prime, they changes. X prime is x cos theta plus y sin theta, etc., etc. Similarly, this Lorentz transformation can also be written as a rotation in two-dimensional plane, time and x plane, but the angle of rotation should be imaginary, right? And that imaginary angle is sometimes called rapidity, which is a function of velocity, and that tells you how rapidly the particle moves from one in one frame relative to the other. That is one thing. And this consideration of this Lorentz transformation as a rotation with imaginary angle is required when you discuss the Poincare group. Okay, now let us define a quantity I, which is x prime 0 square where x prime 0 is the temporal component and x prime 1, x prime 2, x prime 3 all squares and negative. And you can show that this I in both the frame is same. Then t prime square minus x vector square must be equal to t square minus x vector square, right? So now what we do, that means this I can write as x mu, which is equal to x0 square minus x square. This minus is coming because this contravariant vector is x0x, but the covariant is x0 minus x. So then if I take the product of that, then this is x0 square minus x vector square, where x vector contains the x, y, and z component, right? So this I is an invariant quantity. So please note here that a square of the temporal component minus square of the spatial component is always invariant. If I go from one frame to another frame, this quantity will never change, right? And then what we can do, this actually I can also write in the for any other two vector, like mu is a 4 vector, it has a component, let us say a0 as the temporal component and a as a 3 vector. Similarly, b0 is a contravariant vector, b0 is the temporal component and b is a 3 vector. Then mu b mu, I can write this a mu as a mu below subscript, so this is a covariant vector. B mu, I can write this b mu contravariant vector in terms of a covariant vector b nu by multiplying by multiplying this by a matrix G mu nu, which is called a metric tensor, and this J mu nu has a value 1, minus 1, minus 1, minus 1. This is quite obvious. You see, when I am taking this invariant quantity x0 square minus x square, see the temporal component is positive and the spatial component is negative. So a0 b0 is a1 b1 a2 b2 a3 b3, which is sometimes written as a dot b. So when I, without any vector, when I write a dot b, that means it is a 4 vector product. It is a0 b0 temporal component minus the vector product, scalar product of 2 3 vectors. So sometimes it is written that a dot b. Now you see a mu then should be a0 square minus a square. This must also be always a Lorentz invariant quantity because this is temporal component square minus the spatial component square. And this mu sometimes we will write just a square, right? Not in this mu just sorry, just for a square. Now if this a square value is greater than 0, then we call it a time-like component. If it is less than 0, then we will call it a space-like component. If it is equal to 0, then we call it a light-like vector. So this is space time-like 4 vector, space-like 4 vector, and light-like 4 vector. Now let us come to the momentum. See, momentum p square, as I said, a square when I write it is a 4 vector product. So p square will be p mu. So this is p0 square, the temporal component of the 4 momentum, minus p vector square, where p mu I can write as e p, where e is the energy, p is the 3 vector. The temporal component, this is, please note that we'll use this while discussing the Feynman diagrams. So this p0 always need not be equal to the energy of the particle. This will be true only for real particles, right? Real particles. Sometimes they are called on-shell particles. For virtual particles, p0, the temporal component of the 4 vector, need not be equal to the energy of the particle. And we'll see this in some examples. You know, when 2 electron interacts, there will be an exchange of photon between those 2 electrons. The photons photon actually acts as a messenger between 2 electrons. And when those photon will be as a messenger, then you will see those kind of photon can be massive also, right? In that case, the energy momentum relation will not be obeyed. We'll see that. But I'm just telling you that the temporal component need not be always equal to the energy. This will be true only for real particles. For virtual particles or off-shell particles, this condition will be violated. Okay. Please note that this p square equal to p mu, which is energy square minus 3 momentum square, which is equal to rest mass square. So rest mass is always a invariant quantity. So E square minus P square is always a invariant quantity. Note, this is nothing but actually Einstein relation. E square equal to P square, because C is 1 in our unit. E square equal to P square plus M square. This is the Einstein energy momentum relation. Now E square minus P square equal to M square. That is what is. So E square minus P square or rest mass square will be written as a square of the 4 vector. But this,
Professor Alam.
yes, please.
Yeah. Can you repeat the for the case of the virtual particles? I have missed it actually.
Right. So what I am saying, the P mu, the 4 vector, I can write as a temporal component of this 4 vector P0 and the 3 vector, right? Now, this P0, this temporal component of the 4 vector will be equal to energy for the real particles, okay? Or sometimes they are called on-shell particles. But this relation will be violated if you actually consider virtual particles or off-shell particles. Now you may ask, where does such particles appear? So let us consider the scattering of 2 electrons, right? So when 2 electrons, so two electrons are interacting in quantum field theory, you will see there must be a messenger between these 2 electrons. Suppose some electron is here and another electron is there. The other one electron should know that other electron is in its vicinity. So then when they interact, 2 electrons, when they will interact, they will exchange a photon, right? And the exchange photon will be a virtual particles. And we'll see that those virtual particles will not obey this relation. E square equal to P square C square plus M square C4. This Einstein relation is actually valid only for the real particles, for the on-shell particles. But the particles which are acting as a messenger between the 2 particles will never obey such kind of Einstein relations. Those are called virtual particles. I'll give you an example later, okay?
Okay, thank you.
So for the time being, let us just assume that E square equal to P vector square plus M square. This will be valid for real or on-shell particles. But if the particle is virtual, then this will not be valid. So that is the point here. And in Feynman diagrams, you will see there will be a lot of virtual particles. They will appear as a messenger of the interactions, right, in the internal line of the Feynman diagrams, and they will completely violate this relation. Sometimes you will see here 4 momentum square, you see you are getting equal to mass square for the real particle, right? You see, sometimes you will see that this 4 momentum square for the virtual particles may be negative also, right? And in the Rutherford scattering, right? Rutherford scattering the alpha particle with the nucleus, right? When this interaction takes place, it's a electromagnetic interactions. So the photon which is involved in such interactions, that photon will see that it has a 4 momentum square which is even negative. Okay, so this is a very interesting thing we'll learn later. Now we'll also need to define the differential operator del mu. It is ddx mu. With this, note that this x mu is a contravariant vector which has again 2 components, temporal component ddt, and this is the normal gradient, spatial gradient delta. Similarly, del mu is del x mu, which is the temporal component del t, and then other component is minus of the gradient, because contravariant and covariant we have seen they differ by a negative sign. Now, just to fix the notations, and give you the nomenclature, I am discussing this, and there will use a lot of Fourier transform in quantum field theory, because and the Fourier definition of the Fourier transform which I will use is f of x is d4k by 2 pi 4 e to the minus I k dot x. Now, when I am writing here k dot x, it is a 4 vector product. So it is like k0 x0 minus k vector dot x3 vector times gk. And this gk, the inverse Fourier transform, it's just d4x e to the I k dot x f of x. And then the Dirac delta function, delta 4, the 4th Dirac delta function is defined as a Fourier transform of unity, right? So this is for the notation. Now let us go back to the classical theory. Okay. Now already told you about transformation to x nu. Well, lambda mu nu is a 4 by 4 matrix. I have already shown you. Now, suppose I have this part is very important. Suppose I have a scalar function phi of x. It is a scalar function. It is not a vector. It doesn't have a component like, like we have magnetic, vector A, right? This magnetic potential vector A, right? That gives you a vector field, right? But the electrostatic potential is like, it is a scalar field. But then this scalar field and the vector A, they also form a 4 vector. We'll see that. But this function phi x is a pure scalar, right? And it is, for the time being, let us assume that it is a real scalar function. Now, the question which we are asking, that suppose the x transform in this way under Lorentz transformation, how will a scalar function will transform under the Lorentz transformation? So Lorentz transformation of x I know. I want to know how this phi, this scalar function, will transform under this Lorentz transformation. And this is very simple, that this Lorentz transform phi, which is I am calling phi prime, will be the original phi. Only its argument will change, like lambda inverse x. When this lambda inverse is the inverse of this matrix lambda mu nu. Okay. This is I have written in very detail. Today I will send you this note after my lectures. You read it, please. That is if something has happened. That is if we transform a distribution phi x by a Lorentz boost, then the new distribution will have, suppose you have a distribution phi, and that phi has a maxima at certain point x naught. Right? Okay. Now I give a Lorentz transformation to that phi, right? Since it is a scalar function, only its argument will change x. This x, of course, it contains time also. So this x is actually t time and a spatial vector x vector. So this x contains both time and spatial vectors. Now, if we now question is, under Lorentz transformation, how this scalar function will transform, and this is the transformation law. So this is the transformation law for the x, and this is the x4 vector, and this is the transformation law for the scalar phi, right? Now, it is just the transformation will be, I have written very clearly for you that if we transform a distribution phi x by a Lorentz boost, then the new distribution will have a maximum at x equal to lambda x naught if the distribution had a maximum at x naught. So only the maxima of, suppose that you have a scalar function which has a maxima at x naught, right? Then if I transform it, only the maxima will shift. Just simply a shift by this transformation lambda. So this is the transformation law for the scalar function. So this scalar function phi prime is nothing. This transformation is phi lambda inverse x. That is, the transform field phi prime evaluated at boosted point gives the same value as the original field evaluated at the point before boosting. So this is, just simply remember that this is, if x transform in under Lorentz transformation, any scalar function of phi will be transforming like this. Now we want to have a Lagrangian for this scalar function phi, right? We want to have a Lagrangian for this scalar function phi. So this phi, when we have discussed the Lagrangian in the classical mechanics, we had seen that the Lagrangian was a function of q variable coordinate and q dot velocity, right? Similarly, if phi has a if I want to have a Lagrangian density L, right? Then, like yesterday we have discussed how the Lagrangian density comes into the picture for a motion of a one-dimensional string. I have derived that expression. So this L will be a function of phi, like for your classical mechanics q, and like for your classical mechanics q dot, it will be del mu phi. Because I have to have del mu phi, because when I am doing special theory of relativity, I cannot take here a phi dot, because space and time, all the components I have to put in the same footing. So this L will be a function of phi and del mu phi. and I'm saying del mu phi, it contains the derivative with respect to time as well as space. And del mu I have defined. It is like a 4 vector. Temporal component is del t, and the spatial component is a gradient. Now I want to have this L for phi function Lagrangian density for this scalar field phi, and I know how it transforms. I have just told you. Now, what are the terms in such L will come? You see, such that I will get an equation of motion for this L which should be linear. And you know what will happen? This L must be a function of phi square. It should only depend on phi square and del mu phi, del mu phi. So it is quadratic in the function phi and also quadratic in the derivative, right? We'll argue later why I cannot have higher order derivatives. I will come to that. But for the time being, I have L, a phi square, and del mu phi, del mu phi. Now you may ask, what is the point in taking the L like this? This L is invariant under Lorentz transformation. You see, as I said, del mu phi is like a 4 vector, like a 4 vector, contravariant 4 vector, and del mu phi is like a covariant 4 vector. So we have seen that P mu, this will, if I square it, like I have said A square or A mu was A0 square minus A vector square, right? A0 square minus A vector square. So this will also, if I consider del mu phi like a vector, let us say x mu, then this will give me x0 square minus x vector square. So that will be invariant. So this term is invariant, phi square is invariant. So this L which I have written is a Lorentz invariant quantity. This is very important, that this L in relativistic theory, the Lagrangian density must be invariant under Lorentz transformation. So this is the Lagrangian. Only term I can have. And I will argue later, I cannot have a term like phi cube. I cannot have a term for, del mu phi cube. If you write a del mu phi, another derivative, that will not be again Lorentz invariant also. If I have a 3 such term, because this mu has to be always contracted. If I have an open mu, that will not be invariant under Lorentz transformation. Okay, so this is the only possibility. Because I want to, so my purpose is to write down the equation of motion for a scalar field phi. And I know how this scalar field phi will transform, since I know how its argument x transform under the Lorentz transformation. Okay, and since this is, if this is your L, then the action will be L d4x, right? And it is a function of phi and del mu phi. But this d4x is dt and d cube x, which is dt dx dy dz, because L is a density. So this is a density. Because of the density, we have this volume dx dy dz, and S is L dt. That is why this time delta t. Now to find out this station, and now again you have got the action. Now what we have to do? If I want to have the equation of motion for this scalar field, then what I have to do? I have to again find out the extrema of this S phi. So I have to take the derivative of this S with respect to the scalar field phi. And I have given you the definition for the functional derivative. How to take the derivative of S with respect to the function f. And this is the definition. Again, you see, this L I will expand in terms of power of epsilon. First term of this will not have any term dependent on epsilon, right? First term will have L phi del mu phi. And if I take a derivative with del epsilon, that will be 0. Second term will be proportional to epsilon, because that will be del phi, del L, del mu phi times epsilon f, right? Similarly, I will have del L with the derivative with respect to del of del mu phi into epsilon del mu f. So first term, second term will have linear dependence of epsilon. When I take the derivative, then it will be independent of epsilon. The third term will have epsilon square, but when I will take the derivative, I will get a epsilon, and if I take the limit epsilon tends to 0, that will vanish. So only term which will survive is this. If I expand this in Taylor series, I will get only this term, right? Now you see, there is a term here, del L del mu phi. derivative of the Lagrangian with respect to the derivative del mu phi. Derivative with respect to the del mu phi. Right? This term I have, and there is a del mu f. This is the term. This term I will manipulate little bit. What I can do, I can write this as a total derivative del mu of del L del mu phi into f minus a term, which I did in the next slide. Del L del mu phi I can write is a total derivative, right? Minus this term. So if I add this and this term, I'll get this. So what I do in my del S del phi, I replace this by this term. So I get this. Now, you know, this term will be 0 because here is a 4 divergence. You know, whenever you have a 4 divergence, you can use the divergence theorem and make the, like in 3 dimension, we do divergence of something, indication of a volume. We just use the divergence theorem and make it a surface integral. And then that surface I take at very far distance, and that term vanishes. So this term will vanish. So only term which will remain is this. And since del S del Q must be, del S del phi must be equal to 0 because it has to be stationary, then the equation of motion for the phi field, I get del L del phi minus del mu of del L del mu phi is equal to 0. So this is my Euler-Lagrange equation for this scalar field phi, right? Where this L, while I have taken this equation, you know, now I will put, this is the Euler-Lagrange equation. Now I will put this L, right, which I have constructed earlier, A phi square plus B del mu phi. We have, from the consideration of the Lorentz transformation, I will take this L, I can divide this by B and write this term like this. So this is my L, right? Now, like when you have a Lagrangian, right? Lagrangian you have like, which is a function of Q and Q dot, right? From that Lagrangian, I can always, in classical mechanics, I have calculated the conjugate momentum. How? By taking the derivative with respect to Q dot. Q dot is dq dt, right? Similarly, if I have a Lagrangian, if I take, which is a function of phi, like the L was a function of Q in your classical mechanics, if I take a derivative of this L with respect to phi dot, I'll get some variable which I will call the conjugate momentum. Now, please note the towards what I am moving toward the, you know, not today, maybe next day, towards the quantization of the fields. Because you know, if you are in classical mechanics, you have the variable Q, and if you know the Lagrangian, you can calculate P, and then what you did in classical in the quantum mechanics, you promoted this vector P, this momentum P and Q as operators and use the quantization relations. What I have done here, I have got the Lagrangian for this scalar field for the Lorentz invariance by considering the Lorentz invariance. Now, if I have the L, I can take the derivative of that with respect to phi dot, like you did for Q dot, and get a variable which will be like conjugate momentum for the field. So if I know phi and its conjugate momentum, you can proceed towards quantization. But wait, we'll that is far away for now. Okay, but that is the motivation of considering all this. So I am moving towards the quantization, but not today even. Okay, now this pi, if I take this L and take the derivative with respect to this phi dot, which is a time derivative denoted by del 0, I'll get 2 phi dot, right? Now you see, recall again, so I can calculate now the Hamiltonian, right? If you know classical mechanics, we have written H as minus L plus PQ dot. Hamiltonian is minus of the Lagrangian plus momentum and Q dot, right? Now, I have L written here. I have got the conjugate momentum P. So I can, analogously, I can define a Hamiltonian density H minus L plus phi dot, right? Like here you have to use this Legendre transformation, right? In case of making a transition from Lagrangian to Hamiltonian, What we do also in thermodynamics, when you go from the energy to the free energy, F is E minus ST, similar kind of Lorentz, Legendre transformation you use here. And similar, just I'm taking the analogy minus L plus phi dot, because I got phi dot, so I can define the Hamiltonian. So I know the Hamiltonian now. If I put all this, I get the Hamiltonian like this. Now, please note very carefully that this Hamiltonian has a negative term, right? And this is the Hamiltonian which I have got the field phi, right? Now, this Hamiltonian is not positive definite, which we cannot accept. The Hamiltonian should be, for a free field phi, should be positive definite, because I have not introduced an interaction so far. So if I have to have a Hamiltonian which is positive, then A by B whole square must be a negative quantity. Let us call it minus m square, right? So A by B whole square will be minus m square. And now in the Lagrangian, I put L equal to del mu phi, and I had A by B plus A by B whole square, which I put now minus m square. It has to be minus, otherwise for a free field, my Hamiltonian will not be positive definite. At such a situation, some situation H may be negative, which is not allowed for a free particle. With interaction, this may be possible, but now it is not. So this is the Lagrangian density. Then I have got del mu phi minus m square phi square. So I know the L now, right? I have derived the Euler-Lagrange equation. Please note del L del phi, del mu del L del mu phi. Now in this equation, I put that L, this L. What I get is very interesting. Del phi will what? Will give me the phi. Mu phi will go. So what I will have a del mu phi, and that del mu phi, when I take another del mu, so it will be del mu, which will be the D'Lambertian, this square lambda, this D'Lambertian, right? So this will be the equation of this is. So I have put that L in the Euler-Lagrange equation, and this is the equation of motion I have got. And see, this is nothing but the Klein-Gordon equation. Please note here that I have so far never used the word quantum. What I have done here, I have said that I need a Lagrangian for the scalar field. And what was my consideration? By Lagrangian should be invariant under Lorentz transformation. I got the Lagrangian, and then from that Lagrangian I tried to calculate the Hamiltonian, and Hamiltonian, to make the Hamiltonian positive definite, I got the Lagrangian in this particular form. I put the Lagrangian in the Euler-Lagrange equation, which I have also derived. I got the Klein-Gordon equation. So this Klein-Gordon equation is describing it, as I mentioned, this phi, a scalar field phi. So it is a scalar field. It is not the wave function, right? So I have got a scalar field equation for the real scalar field. And this scalar field, if I quantize, then I will get the particles. Which are the particles? The particles which are scalar, like the Higgs. We will discuss this later. But I have never used the word quantum here. I have just said that this is phi is a scalar field, and how it will transform under the Lorentz transformation that I mentioned, and I have got the Klein-Gordon equation. Is it really the Klein-Gordon equation? Let us check. When you derive the Klein-Gordon equation that you wrote h square equal to p square plus m square, c is 1, please remember. Otherwise there will be p square, c square plus m square, c4. And then we promoted them to operator h square, p hat square plus m square, and operated phi on both sides. Put h as I ddt, right? And p as minus I of gradient phi. And you see, this is giving you del plus D'Lambertian plus m square in, operating on phi equal to 0. This is the kth equation which I got here. But here I have used the quantization conditions, right? Now, what is the problem if I do follow this route? Let me discuss that point first. The problem here is that, so suppose this is your Klein-Gordon equation you take from quantum mechanics. Then what you will have the tendency to say this phi is my wave function, right? But here what I did, I am saying it is a classical field. So this is I am saying this is a if I get this way, I'll say this is a wave function. And this wave function can be complex quantity. I can write this phi as a phi1 plus I phi2 by root 2. Wave function is a complex quantity. And for this wave function, right, the way you have derived the probability density and the flux for Schrodinger equation, similar procedure I can follow and then write down the expression for the probability density as well as for the flux. What you do, you multiply this equation by phi star from left, and then also you get an equation for phi star, and that phi star equation you multiply from left by phi and then subtract, and you know how to get it. You get in quantum mechanics, you get the probability density for the Klein-Gordon field in this way, and the flux is this. Note, in Schrodinger equation, it will be rho will be just phi star phi, right? Rho will be just simply phi star phi. Rho will be just simply phi star phi. But here it is phi star del phi del t minus phi del phi star del t, right? And these are coming because Schrodinger equation is first order in time derivative, but Klein-Gordon equation is second order in time derivative, you see. So this is rho and this is j, what you get. And this rho and j, they form, again a 4 vector, where the temporal component is this probability density and j is the flux. And they also obey conservation law del rho del t plus divergence of j equal to 0. Or in 4 vector notation, this conservation law sometimes written as del mu j mu equal to 0. Del mu is the temporal component, ddt, j0 is the j0, here is the rho, you see j0 temporal component is rho, plus divergence of j vector, this j vector. Now, the solution of the Klein-Gordon equation, there goes the time variation of the Schrodinger equation, Klein-Gordon equation will go as e to the minus energy into time. Now, suppose I put this solution in this row. What I get? I get rho equal to E by M phi star phi. What I can write E by M phi mod square. Now this E and Einstein, I have used the Einstein relation. E square equal to P square plus M square. So E can have 2 root plus minus root over P square plus M square. And E admits a negative value. So probability density can be negative. That is not acceptable. So the problem here is that Klein-Gordon equation, if I accept this as a quantum equation, which will describe the motion of a particle in the relativistic domain, I have a problem. Probability density is becoming, is not remaining positive definite. But Einstein relation, so when I'm combining again this Einstein relation relativity from the relativity with the quantum mechanics, I have a problem here. See, that's what I said, that whenever I try to bring the quantum mechanics and the special relativity, I am facing certain problems. Right? Now, you may say that what is there? Let me throw the negative energy states. Right? You can say that I will throw the negative energy state. I will only consider the positive energy states. That you cannot do. Because in quantum mechanics, these operators, they are always Hermitian and they are eigenfunctions, satisfy a relation called completeness relation, right? Or closure relations. This completeness relation, if you want to satisfy, then you have to take all the possible value of each. If you don't take the negative values, you will violate the completeness relations. So you have to accept the negative energy. But if you take the negative energy, probability density is negative, right? So that's a big problem. Now, so you cannot throw the negative energy out from your system. If you take it is negative, probability density is negative, and also other problem is there. See, the nature has the tendency to always occupy the lowest energy state. So if you have a negative energy, if you allow negative energy, any particle, the free particle will try to go to the negative energy states, right? And since I have said that this Klein-Gordon equation is for scalar, right? They are spin, by scalar I mean spin zero particles. Now spin zero particles are bosons. So any number of particles can go to the lowest energy state. For fermions it will not be valid because Pauli exclusion principle will not allow all the particles to go to the one single energy state, So there is a big problem. Neither you can throw the negative energy states, nor you can accept it. Here, people try to argue that negative energy states are not throw it, but that completeness problem will come up. But this is the problem we are facing if we accept the Klein-Gordon equation as a quantum equation. But what I did in my derivation so far, I have never said it is a quantum equation. I have said the phi is a scalar field which transform under Lorentz transformation in such and such way, right? If it does so, then I have constructed a Lagrangian, and if I have a Lagrangian, that way I get this equation, right? Now, let me just comment here this. If you take phi cube term, in the Lagrangian, then when I take the derivative of that Lagrangian with respect to phi, when that L I put in the Euler-Lagrange equation, I'll get if there is a phi cube term, I'll get a phi square term in the equation. And if I have a phi square term in the differential equation, that will give a non-linear equations, right? That will be a non-linear equation. It will not be linear. But my purpose is to get a linear equation for the scalar field phi, right? So that is why I said phi cube term and other term for free field is not accepted. But we'll introduce phi cube and phi 4 term when we will introduce the interaction. For free field, it is not required. So this is the problem of the Klein-Gordon equation. Then what you can do, I'll take little bit of time and go back to my transparency which I discussed yesterday. This doesn't happen in the board. I can keep that in the So you see now the Klein-Gordon equation then is a classical field theoretic equation for the scalar field phi, right? So I am taking this route. Classical field theory, now I have scalar field. Now I'll quantize it, like you did the quantization of the classical mechanics, right? So yesterday, Dr. Jayanta Saha was asking about this route. I'll make a comment there, but I am taking this route and I am comfortable with that because if I take this route, right, then I'll go to the quantum mechanics. From relativistic quantum mechanics I'll get. But in that relativistic quantum mechanics, from there, if I take suppose I have a relativistic quantum mechanics and take the continuum limit and get the quantum field theory, I have a problem. Because Klein-Gordon equation I cannot treat as a quantum equations because it is giving a negative probability density. So better to think that this is a Klein-Gordon equation is a classical equation which describes the motion of scalar field. Like Maxwell equation is classical equations which describes the electric and magnetic fields, right? So that is the route I am going to take. So by this time, that I have got this phi, I have got its conjugate variable. So now, what my intention later will be, not today, to promote them.
Hello, sir.
Yeah.
I am just interrupting a bit.
Please.
As if you were talking that if I am taking the route of quantum mechanics and trying to have a Lorentz invariance, then automatically it encounters the concept of fields because without having the Mond number of particles, I cannot describe the Klein-Gordon equations, which as starting point is a single particle equation, but interpretation comes to in such a way that I need more number of particles to accommodate it. Right?
Okay. So yeah. So let me.
So automatically, the Lorentz invariance with the quantum mechanics have some kind of continuum limit inherently.
Yeah. No, but my point is that if you take the Klein-Gordon equation as a equation which will describe the motion of a particle in the relativistic domain, then there is a problem. Problem is that the probability density is becoming negative. Now,
yes.
probability density is becoming negative. But what I am saying is that I will not talk about quantum mechanics. I will take a scalar field, and I know how a scalar field transforms under Lorentz transformation. I will construct the equation of motion for that field phi. The equation which I am getting is like is a field equation for a scalar field. So this is This equation will describe the motion of scalar field, like Maxwell equation describes the motion of electric field.
Correct.
Scalar field it will describe. Now,
Correct.
so once I quantize this equation, what I will get? I will get the quanta of the field. There is some noise.
No, okay.
Some noise. Okay. So if I quantize the scalar field, right? Then what I'll get, the quanta of that field will be like scalar particle like Higgs. Right? Now, what you are saying about the many particle thing, many particle concept, that is, if I maybe I'll discuss that also. For Dirac equation, when you solve, then what you do, you again get the negative energy solutions. But then what you do, you argue that all my negative energy states are filled up, right? The negative energy states are filled up, and since electrons are fermions, they obey the Pauli exclusion principle. So if my negative energy states are filled up, then no other particle can come there. And to fill up that negative energy states, you need infinite number of particles, because it is negative energy C, infinite number of particles. That's how you introduce the concept of infinite number of particles, infinite degrees of freedom, to save the solution of the Dirac equation.
Correct. That is what I am saying.
Right. But
that means that inherently, as if the quantum equations or the quantum mechanical equations with the Lorentz invariance inherently gives an idea that we need infinite degrees of freedom.
That is right. But then again I will argue that the Dirac equation should also be, as such, should also be treated as a field equation, which will describe the polymer field.
Correct. Because I have started with wave function, and then suddenly it appears that it may be an field also. I mean,
right. So if you start, now the question is, to fill up that infinite number of states in the negative energy C, you need infinite number of particles. Question will be, you started when you start the Dirac equation, you start with a single particle Hamiltonian.
Single particle equation.
Now, who gave you that infinite number of particles to fill up that C?
We have no answer.
That's the contradiction. That's the contradiction. Okay.
Fully understood. Okay. Thank you.
So this is the problem with the Klein-Gordon equation. But in my derivation, what I am arguing is that the Klein-Gordon equation is a field equation for scalar field. Like Maxwell equation is a field equation for the electric and magnetic fields. And similarly, the Dirac equation is also a field equation for spinor field. If I quantize this, Klein-Gordon equation, I'll get the Higgs particle as a quanta of the field. Like if I quantize Maxwell equation, then I get photon as a quanta of the electromagnetic field. And there is a let me tell you also the story that this when Einstein in 1905 described the photoelectric effect by quantizing the electromagnetic field, the Millikan had thought that this is an attack on Maxwell, and then he wanted to prove Einstein wrong. So he did a lot of experiments and tried to show that Einstein is wrong, but he ultimately shown that Einstein is right. So the thing is that what Einstein did is that he showed that Maxwell equations has a domain of validity, right? And you cannot apply it in the to describe the photoelectric effect. And when some people thought that when this is said that it has a limited domain of validity, then that some people thought this is an attack on Maxwell. Okay, but it is not. It is not. Maxwell equation is correct and it is fantastic in its own domain. Okay, so we'll discuss that. But the derivation of the Klein-Gordon equation as a field equation is is simple. Dirac equation is a little bit more complicated. Okay, now I'll also discuss few conservation law. I'll just introduce you to the Noether's theorem again, which I will read in my field theory class, quantum field theory. So I'm just preparing this. So please have some patience. So symmetry and conservation law. And this comes from the Norris theorem. And I'll just give an example from the classical mechanics. Classical mechanics, you know, will give me the action, where L is the Lagrangian. If the action S is unchanged, now what I am making a statement here is that if the action is S is unchanged by changing the X, if action remains unchanged, S remains unchanged by changing X, right? That then there must be some conserved quantity associated with that transformation. That is the statement. Okay. So let me just do one thing. So this is my S action, and I change my X to X plus delta X, right? I do that. So what is the change in action? Delta S is S prime minus S. What is S prime? It is S. So this is a mistake here. This should be L X plus delta X and X dot plus delta X, and dt L X dot X, right? Now suppose you take L, the Lagrangian is mx dot square, the kinetic energy term, minus the potential energy Vx. Now delta X will be L by 2 X plus delta X dot plus delta X dot whole square minus Vx plus delta X minus your original S m by 2 X dot square minus Vx. Now make a expansion and take a term linear up to delta X. You will get change in delta S. Change in delta S, the action as dt mxi dot delta xi dot, because these are three vectors, so they have component x1, x2, x3, xi dot delta xi dot minus dv dxi delta xi. So if when I am making a transformation like x going to x plus delta x, that is changing my Lagrangian, action in by this amount, right? Now this mxi dot delta xi dot, again I can write as a total derivative of xi dot delta xi minus this, right? So xi dot delta xi dot I can replace by this expression in the right hand side. I just replace it here, right? If I replace that there, then what will happen? I will get this expression. Now this is a total time derivative ddt, right? Xi dot delta xi minus mix dot delta xi minus dv dxi. The equation of motion we know is the m xi double dot, double derivative with respect to time, is equal to minus dv dxi. This is the mass into acceleration must be equal to the force dv dx, right? So if I put this equation of motion here, then these two terms vanishes, right? What will remain then? Delta S is equal to T1 to T2 m ddt of xi dot delta xi dot. Now I have said that suppose I make this change in x, and assume that because of that change, whatever change I get, for that there is no change in the action, delta s equal to 0. That means if delta x equal to 0, then m xi dot delta xi dot at t1 and t2 equal to 0. So see, m times xi into delta xi dot is 0. Now consider this transformation x plus x delta x, just to consider a rotation. That is x1 prime is equal to x1 cos theta plus x2 sin theta, and x2 prime will transform like this. For very small theta, delta x1, which is x1 prime minus x1, will be theta into x2, and delta x2 will be minus theta into x1. So the change in the x, delta xi, I can write as epsilon ij times some xj, right? So here when it is I, this is j, you see, and this epsilon ij is a Levis beta, right? So when both the indices are same, it should be 0. So xi will not be, change in xi will not depend on xi because of this rotation. X1 and x2 are connected, x1 is connected, right? So if I put this condition in this, if I put this delta xi here, what I get very interestingly is that if I put there, I get m dxi dt del xi is equal to this. And at the time t1 and t2, this is the m dxi dt xj and m dxj dt dxi. You see, this is like ith velocity component into xj. This is jth velocity component into xi. So this is like vxy minus m vxy. M vx is px into y minus m vy into x. So this is nothing but the component of the electromagnetic angular momentum, right? So angular momentum at time t1, and this is equal to 0 because delta s is 0. So angular momentum at component at time t1 must be equal at time t1 must be equal to time at time t2. That means that the angular momentum component at time t1 is equal to angular momentum time same component at time t2. That means the angular momentum component is not changing with time. What does it say? It says that if the action delta s I have put equal to 0, if the action is invariant under rotation, like this rotation, then angular momentum is a conserved quantity. Angular momentum is a conserved quantity. That's what it says. So this is in the classical mechanics, this is a statement of the Noether's theorem. If you take just a translation, just what you do, you can do a exercise, make x equal to del x plus delta x. Then what you will get? You will get linear momentum as a conserved quantity, right? That is what you will get. So if the statement is there is a group of transformation, and if under that group of transformation the action doesn't change, action remains invariant, then corresponding to that group of transformation there must be a conservation law. Here, if I give a rotation, my angular momentum is a conserved quantity. If I give a translation, the linear momentum will remain conserved. If I give a translation with respect to time, Hamiltonian should remain, the total energy should be conserved. So this is what is for the classical mechanics. But this we have to do for field theory also. And this is bit, involved, but you have to be with me because this is very interesting also. Because you see, after all, the physics today and tomorrow and physics after 10 years, the fundamental physics, the laws of nature should not change. That will be very, 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 a dangerous problem. If every day the laws of physics changes, or if the laws of physics in Calcutta and Bombay becomes different, then there is a problem. So I will show you here that through Noether's theorem, that the physics today and the physics tomorrow and the physics at Calcutta and Mumbai or in any other places or in New York must remain same. Okay. So that is what I am going to do, but this I am going to do for now for the fields, which I did for the classical mechanics. I very quickly did this, and this I will be doing slowly for you for the field. Okay. So let me just ask one thing, that is there any question or should I proceed? I have no problem in going through, but okay, let me proceed. All the steps are done here, so I'll just go through this. Okay. Okay.
Okay, I think.
Okay. So let me just do this part is little, from next day onwards things will be more simpler, but for the sake of completeness I need to do this. So the classical field theory and Noether's theorem. Now consider the x mu prime, where x mu prime, I have defined this as a time component t and 3 vector x. Suppose that becomes x mu plus delta x mu. So I am changing the x to x mu by an increment delta x mu, right? This is the change in x mu. If I make a change in x mu, then suppose I have a coordinate system in x x prime and the unprime, then the measure of the integration d4 x prime, Why I am evaluating d4x prime? Because you know in the action I have the Lagrangian density times d4x. That is why I need to know first how this measure d4x prime changes under this transformation. And I know very well that this I can calculate the Jacobian for this transformation, which will tell me how d4x prime and d4x changes. Right? So and this Jacobian is nothing but the partial derivative of this x prime vector with respect to x. But this, remember, this x prime has a 4 component, time and 3 space component. X has also 4 component, time and 3 space component. And this this Jacobian will be 1 plus derivative with respect to delta mu, del mu of that change delta x mu. Okay, this will be the change in the Jacobian. That will be the Jacobian. Now the classical field phi, which I have defined, which is a function of x, and this I have very clearly mentioned that this is a function, x is time and spatial coordinate, right? So this phi, see, now one interesting thing you must note that phi I can change in 2 ways, right? I can change this phi scalar field, let us say in this way, phi prime going to just by changing the phase of the phi, right? Also I can change the argument x, that will also give some change in the phi. So I can have change in phi in both way, by changing directly the phi like in this way or changing its argument, right? The total change in phi should be, then total change in phi delta phi will be phi prime. I have changed phi to phi prime, and also in argument x to x prime. So I am changing, making the most general change in phi, changing the phi through, let us say, this kind of I alpha phi, and then also changing the argument. I will show you, please keep some patience the next day, that how the conservation of charge comes automatically from the Noether's theorem, and this we need actually. So this is the, we will show you later that this change in phi, if my action will remain invariant under the change in the phase of the phi, then I'll show automatically the charge of the system must be conserved. Okay, but okay. Now this delta phi is this. Now what I have done, I have subtracted and added the term. This is 0 minus phi x prime plus phi x prime. Now you see here I have the argument both x prime, x prime. So this is only this 2 term will give me the change in phi only, which I am denoting by delta phi. So capital delta phi is the total change. This change is only in the phi, like this kind of phase change, and then phi x prime minus x. Here I have taken both phi, not phi prime, but the argument has changed, right? What I can do, this term I can divide by x and multiply, divide by delta x, multiply by delta x, and take the limit delta x tends to 0. Then this will give me a derivative del mu phi, and I have multiplied by delta x, it will remain here. So total change in delta phi will be change in phi, and then change in delta mu phi times change in the argument x mu. Okay. Now this delta phi I can write as phi prime x minus phi x. You see I have not changed the argument, right? And then let me take the derivative of both the side. So del mu of this side is equal to del mu of phi prime minus del mu of phi. But this side is nothing but the change in derivative. So this tells me, this is very important, and this you will need many times. The derivative of the change is equal to change of the derivative. This is a very important result. We will be requiring this. Derivative of the change is equal to change in the derivative. Now let us make the, if I make those transformation, what is the change in the action? The change in the action will be d4 prime x prime, d4 x prime, I have changed x, and then I have changed phi also. So this is the s prime, and this is my s, d4x, l phi del mu phi x mu. So s prime minus s. Now d4x prime, I will put this expression, right? If I put there, I will get just simple multiplication will give me this particular form, right? Now you see here what I can do, this change in the derivative I have shown you is the derivative of the change. So what I can write here, this I can write here, del mu phi, I can write del mu of del phi. So that is what I have done in the next page. That is what a change in the derivative is equal to derivative of the change. And then this derivative of the change I can write again as a total derivative of this quantity minus this term. Okay, so this is equal to this minus this. This simply when you take the derivative of product of two function ddx of f into g, it is like f dg dx plus g df dx. So that is what I have done here. Only the derivative is denoted here by delta mu. Once you put this condition, you know, then this delta, all the steps are done. So if I put this, I will get the change in delta x is like this. Change in delta x is like this. Okay. Now, if you remember that del L del phi minus del mu of del L del mu phi equal to 0 is the equation of motion for the Euler-Lagrange equation for the scalar field. So if I use the equation of motion, then this term vanishes. If this term will vanish, then what I will get? I'll get delta S as this quantity because this term has vanished. Okay. Now, so this term here, what I have done, I have added this term and subtracted this term. So this is just 0, right? But this two term again, why I am doing this, you have this, you see delta phi. If I have a delta x new, that will give me the total changes d phi, which I have done earlier. and you see that system, which is a very important quantity in field theory and also in general relativity. I'll make some comments on that also. Okay, so change in the action because of the change in x and phi, I have got this. Right now, suppose this quantity I have defined as theta mu nu as L minus del mu nu. This is called the energy momentum tensor, and as I said, this has immense importance in quantum field theory, classical field theory, and also in gravity. So next year maybe I'll make some very simple comments on that. This delta S now I can write in this particular form. Again, just follow these steps. This you know, del 4x del mu, I can write this as a surface integral also using the Gauss theorem. Right. Now let us make a change. This delta x mu, the change in the coordinate, I can write this as a some x mu nu tensor. It can be a matrix, and delta mu nu, and delta phi is some capital phi into delta omega mu. Now what we are going to do is that we are going to tell you that if the change in action is equal to 0 because of this change, then there must be a conserved quantity. That is what the Noether's theorem is. So change in action equal to 0 because of these changes, then I will get a conserved quantity. So let us see whether we get it or not. So what I put delta S equal to 0, and then the change in x mu is this, and change in phi in this. This step, I think, one you should do, otherwise you will not have a feeling. And then this equation I can write in this particular fashion. And this quantity which is in the bracket, I define this as a J mu nu is a current, right? So if this quantity is G mu nu, then I can write delta sigma mu, G mu nu equal to 0, right? And this I can actually convert to a volume integration like d4x, and then del mu, G mu nu equal to 0. This you see is a continuity equations, right? Where J mu nu equal to this, which I have defined earlier. So del mu G mu nu equal to 0 is equal to 0 is a conservation equation, and this Q nu, I define a new quantity Q nu, which let us call it a charge, and this charge nothing to do with the electric charge. It could be the total energy of the system also. Just we call it charge in a very generalized sense. So this Q nu I defined as an integration of this current G mu nu over d sigma mu. And remember, G for X was the volume integration. So it is a 4-dimensional system. So when I said d sigma mu, then this sigma mu is actually 3-dimensional quantity. Now, so you have 4 coordinate time x, y, z. So if I consider a plane, if I consider a surface where time equal to constant, then I have 3 variables x, y, z. They will define the surface. That x, y, z surface will be nothing but the volume, right? So for a constant t hypersurface, this will be d cube x g mu nu equal to d cube x into this integration. This the conservation of now what I can do, I can use this equation del mu g mu nu equal to 0. I can break this is a del mu del 0 component, time component, and then there is a spatial component I can take. Now you see the spatial component, again I can convert this by Gaussian, I can use the Gauss theorem to convert this to a surface integration, and I can take this surface far away so that this surface term vanishes. If that surface term vanishes, then I have del 0 j nu 0 d cube x equal to 0. Now ddt, so this del 0 is nothing but ddt, and this del 0 d cube x equal to 0, and this quantity I have defined as q nu, total charge. I said charge, but this charge is not the electric charge. So ddt of q nu equal to 0, and this is the Noether's theorem. So what I said here in a simple word, all the steps are done there. Board would have helped me a lot. What I have done here is that I have changed the phi and x, and basically I have calculated the change in the action. And I said if the change in the action is 0, then there must be a conserved quantity, some quantity which time derivative will be 0, and that is what I have got through that calculation. Okay, now just let me give you a simple example before I close today. An example of transformation. Suppose I give a change only the x coordinate, del x mu equal to epsilon mu. So phi I am not changing, right? And when I am saying del x mu equal to epsilon mu, see there is a change in x is equal to epsilon mu. So if I take the 0th component here, del x0 is nothing but, that is the temporal component. Change in time will be epsilon 0, and change, if I take mu equal to 1, 2, 3, that will give me the spatial change. So if I take mu equal to 0, that will give me the change because of the time, because mu equal to 0 is the temporal component. And if I take mu equal to spatial like 1, 2, 3, that will give me the translation in space. So mu equal to 0 will give me the translation in time, when mu equal to 1, 2, 3 will give me translation in space. Now space-time translation should not change the physics. The physics, if I have a system, hydrogen atom which is at Calcutta, if I make a transformation and take it to Bhubaneswar, the physics should not change, right? Or if I have hydrogen atom today, tomorrow it should not change. Noether's theorem is nothing but the mathematical statement of this conservation law, of this symmetry. So delta x mu equal to, if I take this is a mu equal to 0, that will tell me that physics today, tomorrow, day after will not change. If I take this mu equal to 1, 2, 3, that will tell me that physics in Calcutta, Bhubaneswar, Bombay should be same. Under translation, spatial translation, it should not change. So that is what I am doing here. So if you put now this delta x mu equal to epsilon mu in the original expression for g mu nu, you will see that you are getting g mu nu is equal to theta mu nu. Now theta mu nu you get here. Now you see I have derived this time derivative of this 0th component of new integration of dqx is equal to 0. This is what I said is this one. This is what I have already done. This is the Noether's theorem. And for this particular translation, right, translation in space and time, I got this, right? Now you see, suppose I take mu equal to 0, I take nu also equal to 0. So this is theta 0, 0. Now theta, you see I have defined here. I have defined here. I will show you so that you can, some of you, at least the young student, can work it out. All the steps are done. I will be happy if the students at least do this. So the theta 0, 0, from here, So theta 0, 0 means I will take mu equal to 0, nu equal to 0, 0, 0. 0, 0 will give me just minus L. Okay. So that what I do here, today's lecture will be a bit maybe not very interesting, but it is very important. But if you do it by your hand, it will be extremely interesting. So theta 0, 0, I put here, you know, now this you see del L delta del 0 phi. So this del 0 phi is nothing but phi dot, and this is also phi dot minus L. And del L del phi dot, remember del L del Q dot was your momentum. Del L del phi dot must be a conjugate momentum pi here. Phi dot is there, minus L. Compare this with your classical mechanics. H equal to P Q dot minus L. This is pi, which is conjugate momentum, phi dot coordinate like Q dot minus L d cube x, right? So this is nothing but then the Hamiltonian density. Like H is P Q dot minus L is Hamiltonian. So phi dot minus L is Hamiltonian. Integration over x. So Hamiltonian density d cube over its integration is nothing but the total energy. Now you see that if I take nu equal to 0, then I have shown you that theta 0, 0 dqx is nothing but the total energy. So this is saying ddt of the total energy is equal to 0. That it says the conservation of energy. It says the conservation of energy. Why? Because I have taken mu equal to 0. That I have taken mu equal to 0. That means I have given a translation. I have mu equal to 0 is the time. So I have given a translation with respect to time, and I saw that the total energy of the system is conserved. Please note one more interesting thing is that theta, though I have said it is a charge, but it is really not charge. It is a charge in name is given in a very generalized sense. It is actually theta 0, 0 is the total energy of the system or the total Hamiltonian of the system. So if under time translation, if my action remains unchanged, then total energy will be conserved. If under space translation, if my action remains invariant, if delta S is 0, then I can show you that total momentum will be conserved, and so on. So this is a very important theorem. You must, at least all of you should know this, especially the young student. And it is in the classical mechanics. There I have given a new example, and also they are in the classical in classical field theory also. So today I'll stop here, and next day I will almost equipped to go to the quantum field theory. Okay, so let me know if you have any question.
And is there any question from the audience, participants?
Yes, sir, I have a question.
Okay, put forward.
In classical mechanics, we have seen that we can add a total derivative of function to a Lagrangian, and our equation of motion is constant. Can we do this same for this field theory?
Absolutely, and I'll do it in the next day. As I said, when I define this theta mu nu, the energy momentum tensor, I'll do that in the next day and make a few comments how it is useful for gravity also. Yeah, okay. It can be done, and I'll do in the next day. That is my plan next day, and after that I'll quantize the field.
Okay, thank you, sir.
But let me know whether it is useful or not, because that's what at the end of the day matters.
Okay.
This Neudard's theorem, the board would have helped me, but anyway, we have to go do like this.
Okay.
So,
Okay,
sir, I think it is a, yes.
Okay. Carry on. Jayanto, carry on.
Oh, no, I think this is perfectly okay. I mean, having the lecture notes, it will be easier for us to do the calculations. Otherwise, the underlying principles are perfectly clear.
Okay,
perfectly
very good.
Clear.
So I'll send you the notes this evening itself.
Yes, just to brush up the mathematics, it would be helpful.
Sure, that is very important. That is, that mathematics part. If you do, then I can tell you personally, it's extremely interesting to see that if I translate something in time and it gives me a conserved quantity, it's marvelous. I mean,
yes.
No, Professor Alam, I must say your lecture is excellent. I think many of the students will be benefited.
Thank
Yeah.
you. And the most interesting thing is that in quantum field theory, the question like this, I mean, Dr. Jayanta Shah has indicated that. I'll explain this in due course of time. Suppose you have an electron which you have just produced in your lab today, and the electron which is, let us say, coming from the supernova or from the very early universe, why the two electron is exactly same? I mean, the electron which you have produced today in the lab, why it doesn't have a error in comparison to one which you have produced in the supernova? Why it is exactly same? And quantum field theory is the theory which can answer this kind of questions. So, and since you have mentioned electron and Dirac equations, Dr. Jayanta Shah, I'll come back to that, but little later.
Yes, okay.
Sir, I want to comment here, sir. This, in case of an atomic electron and electron coming out from nucleus, the beta particle, so they are mostly identical, but they differ only in energy, right? Sir?
No, by energy will be different, but why their spin, their charge, their mass, the intrinsic properties of the electron is same. Energy you can externally change by accelerating it or decelerating it. You can change. So why the electron which is produced in the early universe is same as which you are producing today in the laboratory? Why it is so? I mean, what exactly same? I mean, you cannot produce an electron which has a properties which will have a little error compared to the one which was created in the early universe, let us say. So what is that? Actually, that is what Dr. Jayanta Shah's question will be answered in the due course. That in quantum field theory, vacuum, vacuum is not empty. Vacuum is not. It is. And you can see very simply from the energy momentum uncertainty relation, delta E, delta T is, let us say, H. Okay. Now, if you define vacuum as a space, region in space which is empty of energy or mass, because they are equivalent, as Einstein told us. So if you want to make, if you write down delta T is H bar by delta E, that will mean that vacuum will mean that you have to make delta E equal to 0, right? In some region. But that will take delta T to infinity. So it will take infinite amount of time to make any vacuum. So vacuum, quantum mechanics does not allow you any space, any region which will be devoid of any matter.
So I have a queries only.
Please.
That in the you have said that the existence of negative energy is impossible, right? So we see in the Swiss quantum state.
This negative energy solutions will be associated with the antiparticles. I'll come to these discussions when I'll quantize the field. But what I meant today actually is that in regard to Dr. Jayanta Shah's question is that, so when you solve the Dirac equation, what you do, you write down the Hamiltonian for a single particle, like H equal to alpha dot T plus beta M, right? And then you give a psi in both sides and solve the Dirac equation and get a solution.
Yes.
And you get both positive and negative energy solution. Now, negative energy particle will have the tendency always to go to the, and negative energy solution, negative energy has no lower limit. It can go up to minus infinity. So if you allow the negative energy solutions, then all the particles will try to go to the lowest possible energy states. But then electrons are fermions. So Pauli exclusion principle has to be obeyed there. So what will happen there is that what was the argument given, that then all the negative energy states are filled up by the electrons. So any electron from positive energy electron cannot jump there because states are filled, and Pauli exclusion principle will not allow any extra electron there. So to get the negative energy solutions, you need to have a sea of electrons. The argument is that you started the Hamilton Dirac equation is the single electron. Now to save the solution, you need infinite number of electrons. Who gave you that? This is the inconsistency with the solutions of the Dirac equations. But once we treat the Dirac equation, once we quantize these Dirac equations, we'll get the antiparticles of the electrons, positrons, which will be associated with the negative energy solutions, and the problem will be solved.
Okay.
We'll discuss that.
Yeah. Okay. Okay.
Is there any more question? I think.
Yes, I actually have one. Okay. Professor Alam, I had a question regarding the Lagrangian density. Okay. Can we introduce a higher order special derivative in Lagrangian density? And if we can, how it will change the dynamics and all?
No, I actually missed the first part. Please, can you please repeat?
Can we introduce higher order special derivative in Lagrangian density?
Well, that will not keep your equation linear. Because you know the Euler-Lagrange equation which I have got, I have just I don't know. I'll show you next day that you can that will if you see you have to form a quantity which is Lorentz invariant. So you can have del mu phi.
Yes.
Quadratic in derivative. You cannot have cubic term in the derivative because that will have del mu phi if you write. And if you have a del mu phi, that term will not remain invariant under Lorentz transformation. Lorentz scalars will always have that mu and nu index contracted, equal number of mu as superscript and subscript. Now, if you take so third order is not allowed. If you take fourth order, then what will happen? You will get an equation which will be a non-linear equation, not a linear equation.
Okay. Thank you.
Okay.
Okay, sir. I think your notes, what you have shared with us,
I'll send you. Actually, during the lecture, I could have sent you right now, but there was a mistake. In place of L, I have written S. I'll write that and send you.
You have mentioned that also.
Yeah.
Sir, actually, your note is self-explanatory, I think, and you have very nicely explained everything. And still, I request on part of our particular for students that if you can suggest a book for beginners only.
Right. In the note, I'll write some name of some book. Basically, it's not a single book. It is, but certainly, it is. Of course, this is not a new discovery. I am taking from books, but somehow I have also mixed up my own experience also. So it's a composite thing, but the good book will be Peskin and Schrader and Ryder. But the problem is that the quantum field theory I'll discuss here is for the canonical quantizations. There is a path integral approach also that I'll indicate if you are interested later. The good book will be Peskin, but I'll write down the name of the book in the note itself.
Okay, sir. Then if there is no more question, then I should thank Professor Alam for this day 2 lecture. And our next lecture will be on 27th November, Friday, at the same time. So,
it's my pleasure.
Okay. For this evening, thank you very much, everyone.
Thank you. Thank you all, and good night.
Okay. Good night to everybody.
Good night.
Thank you.
ওকে স্যার, তাহলে আমি করছি, স্টপ করছি রেকর্ডিং।
ওটাকে রেকর্ডিংটা অফ করে দাও।
হ্যাঁ।